introduce our presenter for today. Jane, go ahead.
Very happy to see you here, including those who found your way to the link. We don't know what's going on, but we're going to try to work on it to figure it out. But always know that you can go to the link online, or you can go to the link if you maintain your emails. You can go to one used before. We're very happy to welcome you and to our speaker, Lori Dengler, who's an emeritus professor of geology at Cal Poly Humboldt and an expert in tsunami and earthquake hazards. Since retiring in 2015, she continues to work on earthquake and tsunami preparedness efforts on the North Coast through the Redwood Coast Tsunami Work Group, and nationally as a member of NOAA's Tsunami Science Technical Advisory Panel. She writes the weekly Not My Fault column in the Times Standard and recently spearheaded the newest edition of Living on Shaky Ground. We're always happy to hear her. I try to engage her both spring and fall semesters. She's allowed a summer off, but we love having you here, Laurie. It's all yours. Thank you.
Okay, can everyone hear me?
Yes.
Good. All right. So this is a talk that's near and dear to my heart, and it's been in the making for about 3 decades. Originally was going to give it last year, but then we had that darn earthquake in December. So last spring got bumped. But since then, we've actually polished the story quite a bit. So I hope you will enjoy this cold case revisiting of the 1954 earthquake. So we got the land acknowledgement before, but when it comes to earthquakes, it's far more important than just thinking about people who lived here before. We have an enormous number of tribal nations that were in our area. In fact, the most dense area, certainly of different tribal groups in California, and arguably pretty much throughout the United States, reflecting our diverse habitats and really rich resources. These people were here for thousands of years and experienced many more earthquakes than you have, some of which became part of their oral history. If we had listened a little more carefully to them, we might actually have better answers to the earthquakes like 1954 that I'll be talking about today. So this has been a real team effort, and you'll notice that I'm pretty far down in the list of authors on our recent paper published in August that really tries to wrap up the story of this, what turned out to be a far more important earthquake than I ever thought at the beginning of this process. So I'm a relatively minor player in this group of all-stars. If you have attended any of my previous talks or have lived on the North Coast for more than a few months, you know that this is a shaky place. Since 1900, we've had about 250 earthquakes of magnitude 5 or larger. 53 larger than magnitude 6, 9 larger than magnitude 7. And the largest earthquake in our written historic record is 1906, magnitude 7.9. You might say, oh, I thought that was in San Francisco. It ruptured from near Santa Cruz all the way up to the Mendocino Triple Junction you see on this map, and caused more widespread damage here than any of our other more recent historic earthquakes. 70 earthquakes have caused damage, 9 caused major damage, and we've had 2 deaths directly related to shaking. There were 2 deaths in 2022. Those were medical related, fear exacerbated, but not related directly to earthquake damage. Nearly half of the seismic energy released in the lower 48 states comes from right here. If we look at a timeline of earthquakes since 1900, and this is only showing earthquakes of magnitude 6 and larger, you'll notice that we've had a lot of them. We've had bigger earthquakes than what happened in 1954. We've had more damaging earthquakes than what happened in 1954, as shown by the arrow here. So I'm going to try to convince you over the next hour that 1954 is special and certainly worthy of special treatment. Importance when it comes to earthquakes has to do with location, location, location. So let's take a brief geographic look at the North Coast region. And if we were to drain all the water out of the ocean, you would notice some striking features. So off of our coast is this relatively shallow area of the seafloor that we call the Gorda Basin, named by the Portuguese fishermen who moved into this area in the 1800s and called it the Fat Basin because it was such a great place to fish. To the south, we have the Gorda Escarpment, which is a phenomenal ledge where we go from the relatively shallow waters of the Gorda Basin into the really deep Pacific. And notice how odd the continental shelf comes down here to the Triple Junction, and then it's kind of like severed and squeezed way out. That's not a natural sort of feature, and we can thank our tectonic environment for causing that. So in the last 30, 40 years, we have a much better understanding of what causes the features of the ocean basin and adjacent land. Plate tectonics, and when we look at the plate picture in our area, this shallow part is the Gorda Plate, deeper, the Pacific Plate to the south and to the west. We have a spreading center, the Gorda Spreading Center offshore. We have the Cascadia Subduction Zone, which will come into this story again later, where the Gorda Plate is diving beneath the North American Plate. And then this sort of fuzzy place that we call the Mendocino Triple Junction, which produces a whole lot of earthquakes. This is a map, a USGS map of earthquakes of magnitude 5 and larger since 1990. Actually, it should be since 1900. There was an error I didn't correct. So going back to 1900, you can see that there are a whole lot of earthquakes in this area, and I've felt quite a few of them. Many are concentrated down here in the Triple Junction region. We have quite a few, like last December's earthquake on the Mendocino Fault. But we also have quite a few earthquakes scattered throughout the Gorda Plate. And you'll notice that there are very, very few inland. Now, when we look at this same data set, but only the shallower earthquakes less than 9 miles deep, we find that essentially all of the inland earthquakes disappear, with the exception of a handful, and especially 1992, that 7.2 Cape Mendocino earthquake that was located in the Triple Junction region. So offshore, we have quite a few shallow earthquakes, which isn't surprising because the Gorda Plate, where a lot of these earthquakes are happening, makes up most of this seafloor. Let's kind of look at a very simplistic cartoon of the plates in our area. So if we have the bird's eye view, we're looking down on the western US. most of what we're looking on land is the North American plate. Offshore, most of it is the Pacific plate. Now, there is part of California that is west of the North American plate. Not going to pay too much attention to that in this talk, separated by the San Andreas Fault. So we've got the volcanoes that are part of the Cascade Range, and then green and the green Gorda Plate, which is just really the southern piece of the Juan de Fuca. I'm going to be using these color schemes: green for the Gorda, Juan de Fuca, red for North America throughout, which hopefully will make things clearer. Now, if we take a cross section, if we sliced right through here, this is really cartoony. Offshore, we have the Gorda Ridge there, where new oceanic plate is being created. And then we have this conveyor belt where the Gorda Plate is being pulled by gravity beneath the North American edge. Those properties create the volcanoes like Mount Shasta. But I'm not going to be interested in the volcanoes today. We're going to really just be focusing on the little edge where we live in. Now, we call this the Cascadia subduction zone. It extends all the way up to Vancouver Island, Canada. And it certainly has the potential to produce great earthquakes. So let's just zoom in to kind of where we live. And again, this is a pure cartoon representation. We are sitting on the North American plate. If I were to drill straight down beneath me where I'm sitting, I would hit that green Gorda Plate, though I don't think it's green, about 8 miles beneath where I'm sitting. So all earthquakes that are deeper than about 8 or so miles are occurring within the Gorda Plate. And that was an example of the December 20th, 2022 earthquake. It was centered kind of over there, this kind of area. We do have some shallow earthquakes. We'll call this earthquake zone up here above this interface very shallow. And there are a number of map faults in it that I'll show you in a bit. Then we have the actual interface itself, the black line, which I'd call shallow. It's on the order of 7 to 9 miles, getting shallower, obviously, as you go to the west. And then this zone of relatively deeper earthquakes that are basically more than 10 miles deep that are in the slab. Fortunately, we've got good data now, especially since 1980. And one of the co-authors on this project, Anthony Lomax, is just a whiz at relocating earthquakes. And what I've done is taken one of his cross sections, similar to the cross section we were just looking at, that shows actual earthquakes that have been recorded since 1980. And we find that almost all of them are down here in the green. There's a smattering of stuff up here in the red, small magnitudes for the most part. We're talking about magnitude 2s and 3s. No earthquakes actually on the interface, with that one exception of the 1992 Cape Mendocino earthquake in the Triple Junction area. And lots of deeper earthquakes on faults within the subducting Gorda slab. I'm going to turn the clock back to 1954 to sort of understand what's going on in terms of seismology, earthquake awareness. We need to think in 1954 terms. Certainly California was a leader in seismology in 1954. We had 2 seismic networks, roughly a dozen seismic stations, well, about a dozen and a half. Caltech operated 7 stations in Southern California at the time. Berkeley operated 11 stations. There were only 2 permanent stations on the North Coast, no such things as telemetry at that time, no such thing as atomic clocks. So every seismic station had their own internal clock that you tried to coordinate using a radio time signal. This was the early days of strong motion instruments, and we're very fortunate the Coast and Geodetic Survey had instruments in Eureka and Ferndale. Now, we did have an understanding of earthquake size. Richter had developed the Richter scale in 1935, and it had been adapted to include larger earthquakes in the 1950s. We also had a second scale called the Modified Mercalli Intensity Scale, which measured relative shaking strength. That had been adopted in 1931. And over here, I've got an example, a simplified example, where if we are talking about an intensity 6, felt by all, many frightened and run outdoors. We really hope you don't run outdoors anymore. Some heavy furniture moved and so forth. So this is the way in 1950 we would sort of describe the felt effects. At that time, the USGS had nothing to do with earthquakes. It was under the auspices of the US Coast and Geodetic Survey, part of the Department of Commerce. Excuse my cheering section. That is, unfortunately, my dog welcoming my husband home in the background, but we'll charge on. She'll be quiet in a minute. So the state of earthquake awareness in 1954 was actually very high. In 1952, in July of 1952, a very large earthquake had occurred in South Central California in Kern County. At the time, it was estimated a 7.5. We now rate it a 7.3. It killed 14 and caused $70 million in damages. It was a very newsworthy event. And this particular photo illustrates one of the features of the modified Mercalli scale, which was thought to represent extremely strong ground motions, namely railroad tracks that had been bent. More recent thinking shows that it turns out it's a lot easier to bend railroad tracks than we thought. But anyway, it was a dramatic earthquake. If you've been following any of my newspaper columns, you note that I've been talking about Kamchatka quite a bit. Back in July, we had a magnitude 8.8 that sent a tsunami our way. We had a tsunami warning. Well, in 1952, there was a bigger earthquake. At the time, estimated as an 8.2, we now put it as a 9.0. It produced a Pacific-wide tsunami. And then one of the most interesting earthquakes occurred, a sequence, the 2 biggest earthquakes in the sequence occurred only 4 days before the 1954 quake on the North Coast. The Fairview Peak Dixie Valley earthquake, sort of doublet, magnitude 7.1 and 6.9. Fortunately, a very remote area, very little damage, but it produced spectacular faulting like this normal fault. And you can see that the outhouse is there relative to the cabin, which wouldn't be very convenient. On the North Coast, there had been frequent earthquakes before 1954. This shows an earthquake timeline relative to intensity. In other words, not magnitude, but how strongly the ground shook. And you can see we had quite a few earthquakes. There's 1906. We had some very large earthquakes in the early part of the century. And then again, 1932, the second earthquake that actually caused a shaking death. But in the 22 years between 1932 and 1954, things had been relatively modest. So a couple of earthquakes that shook some items off shelves. But for the most part, earthquakes were probably not at the top of people's minds. So what did we know about the 54 earthquake at the time? I'll get in more into the various locations, but this is where it shows up in the USGS catalog today. And if you pull up the event information, you'll see that it's listed with a magnitude, a location, but no depth. Why is there no depth? Well, it turns out determining depths is sort of difficult when you don't have a dense network of seismic stations around it. And if you look on the map of earthquakes that were shallow, it doesn't show up at all because we didn't know the depth. But there were things we do know about it, and we knew about it in the 1950s. It was felt over a very large area. So this is the felt map that was put together based on damage and based on people's responses to how they felt or experienced the earthquake. And again, this is in this modified Mercalli scale. And I'm using red to denote 7 or higher, basically chimneys knocked down. And then blue on this is map as weak. This was felt well into Central Oregon, and it was felt south of the San Francisco Bay Area. There was one death. An employee, Carl Wilkerson, of the lumber company in Eureka, it was located where the Bayshore Mall is today, who was having lunch. This earthquake happened just before noon on a Tuesday, 4 days before Christmas. And he was hurled into a log pond by the shaking motion, hit his head, and unfortunately drowned. At least 50 injuries, supposedly none serious, hundreds of toppled chimneys. The Humboldt County Courthouse was condemned, at least $2 million in 1954 damages. It ruptured the main water transmission line from Swayze Dam, damaged other parts of the water system, and there were reports from fishermen of the Mad River flowing backwards. Well covered by local and regional media. Teams of engineers came to assess the damage, primarily in Eureka. This is a map that I found in the Berkeley's Nisi Library of photos. Unfortunately, I mean, this documents all the places they examined. I was not able to find the actual engineering reports, but all of these red spots are where significant structural damage occurred. In other words, not just stuff falling off shelves, but the actual structures damaged. So the crests 5 and 10 and dailies were sort of the poster children of the damage. But looking up F Street in Eureka, you can actually see there's quite a bit of damage in Eureka. And here's the Humboldt County Courthouse. I first became acquainted with courthouse when I was studying the effects of the 1906 earthquake in Humboldt County. It was quite a structure located on the same site as today's courthouse. It had this elaborate, it had been built, completed in 1889, had this elaborate tower, and the 1906 earthquake had bent the statue of Minerva at the top. It had actually caused some damage in the courthouse as well. But it was patched together, continued to be used. There was a big fire in the 1920s, after which this whole upper structure was removed. But in 1954, it was still being used as the courthouse. After the earthquake, you can see all of these cracks in the upper floors, and it was immediately condemned. 2 years later, it was demolished. and plans drawn up for our present courthouse. Most common type of damage were chimneys. One report I saw estimated more than 500 chimneys damaged in Eureka alone. Some of the damage was the actual top part falling down. You can see the pile of bricks. These are all photographs from Eureka. You can see this car where a large block has fallen off. But there are also many cases of what's called a chimney being loosened. So this is a loosened chimney. Obviously not good, because the next temblor could certainly knock it over. A lot of twisting chimneys. One of the reasons we don't see quite so many chimneys in the area anymore, but many were rebuilt, and many then again fell down in the 2010 earthquake. The water damage, the waterline damage was difficult. Here shows the water line. At that time, water came from the Swayze Dam up the Mad River. You can see just how large this pipe was that carried the water. And it was severely damaged where it crossed the freshwater slough. There was a reservoir that was damaged. Here we're looking, and you can see the two different water levels. Down here, all of this water has drained relative to the side on the right. Fortunately, they were able to patch it together pretty quickly, and so there was not a dearth of water. Non-structural damage was ubiquitous, and these are photographs taken both by newspapers at the area and also in post-reconnaissance. Pretty much everything off shelves in markets, lots of broken windows, lumber decks that collapsed. The Coast and Geodetic Survey conducted an intensity survey where a questionnaire, they actually posted the questionnaire in the newspaper, but it asked a number of questions. Did it awaken you? Were you frightened? Did you hear rattling? Did you see trees shaking? And so forth. And then that information was tabulated. So here's an example for the report in Eureka from the postmaster in the Eureka post office at that time. Motion rapid, felt by and frightened all, hanging objects swung, dishes and windows broken, damage considerable. In Corbel, where we first thought the earthquake might be located, again, lots of indications of strong ground motion. Large piles of lumber tumbled, lights swung violently, lamps tipped over, and so forth. I did manage to come up with a copy of the Berkeley Seismographic Station's annual, well, decade report for the 1950s. You can see the earthquake right there. Zoom in. Now, I'll notice it looks like they're on a grid because at that time they rounded off the latitude and longitudes. But you can see the earthquake clearly looks like it's onshore, which makes it very interesting. Since 1954, a number of different groups have looked into this earthquake. There were several publications in the few years afterwards, including Don Toscher, who was my very first boss. In 1968, I worked for him at the Earthquake Mechanism Laboratory under the Department of Commerce. I worked on 1966 aftershocks at that time. He did his dissertation, and this earthquake was included in that study. All all of these round circles show various different locations. And you can see they're kind of all over the map, anywhere from south of Eureka to east of Willow Creek to east of McKinleyville. The white circles are all just locations. These three darker ones were attempts to estimate a depth. How do you figure out the depth of an earthquake? Well, one of the best ways to do it is to have seismographs that clearly record both the P and the S wave. And we did have a group, we didn't have a good seismic network in 1954. Our first dense network was established in 1974. It was called the Humboldt Bay Network. And its specific purpose was to monitor seismicity with regards to the safety of the Humboldt Bay nuclear power plant. You can look in the OLLI Brown Bay archives and we'll find a talk that I gave a couple of years ago on the PG&E plant. As part of the networks, and this is the original group, and there's a very young Bob McPherson, who I've learned more about North Coast geology and seismology than from anyone else. As part of the seismic network's efforts, they re-examined old earthquakes. And this is the first real published evidence that this earthquake was, where it was located, and how shallow it was. They drew arcs from 3 stations, one at Arcata, one in Eureka, and one down here in Ferndale, where these arcs, based on the P time and the P and the S time, they made an estimate that this was not a deeper earthquake, that this earthquake was likely shallower than 9 miles. Shallow now, today, means a whole lot to us because it means that it could have been centered on one of the faults in the North American plate. So here's a fault map of what we call the Mad River Fault Zone. And all of these lines with little teeth on it are map faults. So most of you listening to me are probably pretty close to one of those faults. I know I am. And they're all part of the deformation that this subduction process causes. And so we began to think maybe 1954 was located on one of these surface faults. In 1992, I worked with Gary Carver and Bob McPherson to compile a publication summarizing earthquake sources in our area. It's called Sources of North Coast Seismicity, and I can link you to a PDF if you're interested in learning more. And we put out this figure showing all the different places where we get earthquakes from. Down here on the San Andreas Fault, over here on the Mendocino Fault, lots of earthquakes in the Gorda Plate, the Great Cascadia Subduction Zone earthquakes, where we think we're talking about earthquakes of 8.5 and larger. Those have not happened in written historic times. And then there's this little zone here of what we call the surface faulting, or these North American plate faults. And this is what we wrote about it in the 1992 paper. Only one damaging event, December 21st, 1954, appears to have been located within the overriding North American plate. We didn't have great evidence for it. And over the years, that thought has been in the back of my mind. Can I find somebody to help us really figure out where 54 was located? Peggy Hellweg to the rescue. Peggy, I first met probably 20 years ago when she was running the Berkeley Seismic Network. She's an expert on instruments. She's an expert on data storage, where things are archived, and she knows everybody in the seismology world. So she fortunately retired from that position a couple of years ago. And I've been saying, Peggy, can you help us figure out where this earthquake is? And fortunately, she took on the challenge, put together a great team of people, collected original data, found folks to relocate the earthquake, found folks to determine what kind of faulting it was. I collected recollections of people who experienced the earthquake. We had someone who dug up the old summaries of felt reports, published a new shake map, and most importantly of all, actually got it out into the literature. So here's an example of the original records. These are the two strong motion instruments. Here we're looking up here at Eureka. Down here is the one in Ferndale. And you can see how the signal starts out relatively small. Those are the P waves, and then gets much stronger. Those are the S waves. So the difference in time between P and S helps tell you how far away it is. Peggy also managed to find all of the original Berkeley phase picks. In other words, the grad students who work at the time looking at all the actual analog records and estimate the time of arrival of the P wave, the S wave, and others. There's an abundance of records if you are persistent and know where to look. Here is an example, though, of just how hard it is to kind of decipher it. This is the record from Arcata, from Founders Hall. And this is the east-west. It's a horizontal record. And you can see down here at the bottom, kind of long wiggles. You can also see traces going up and down. Actually, when the earthquake started, and here's a blow up of when the earthquake started, the pen was flying so rapidly that it's not leaving. This is actually a light. It's a light shining on photographic paper, so it's not really a pen, but it's going back and forth so fast that it's not even leaving a trace. We just see these little bits of it. And then you can see this longer period signal. That's actually later. Usually these go from top to bottom, and you can see how these little minute marks are offset right here. That's probably because there was a power outage. And so it actually changed the alignment of the instrument. And so these later surface waves appear to be coming in earlier. This is some of what you've got to deal with when you're trying to study old print records. Fortunately, we had enough data that Peggy was able to send all these times and pics to Anthony Lomax, who is an absolutely brilliant, I call him a seismic statistician, because he has developed these methods of taking a lot of data and developing probability clouds. He calls it the non-lin location program algorithm. And here are three different views of his results. So here we're looking the bird's eye view of looking at all. I mean, he took this data and basically took different test depths, used the modern velocity structure, and he comes up with this cloud of possible locations. But right here where the X is where everything coalesces. It might be a little easier to see on this vertical section looking from the south. So you can see how there's this cloud of depths, but this is where everything coalesces. And again, this is looking from an east-west perspective. And again, the best location. So he came up with an epicenter with a depth and a big uncertainty, 7 miles horizontally, 9 miles vertically. But that's actually not bad. So here's where that epicenter is, right where that pin is. In between Arcata and Blue Lake. As I say, when we first started working on it, I called it the Blue Lake earthquake. Then we called it the Corbel earthquake. But now we call it the Fickle Hill earthquake because its closest, the closest geographic feature is Fickle Hill, named after the Fickle family, Dr. William Young Fickle, who ran a shingle mill on Fickle Hill Road. Fortunately, depth is not the only thing we have to work with. We can also figure out the kind of faulting. Now, in 1954, no one talked about focal mechanisms. That idea wasn't really developed until the 60s. But now we can go back and look at these old seismograms and figure out how the ground moved when the first seismic wave reached there. So over here on the left is a simplified introduction to what I call beach balls, how fault movement pushes seismic waves up in some areas and pulls them down in others. So when we have a strike slip fault, like what happened last December, we have these 4 distinct quadrants where we have areas of push and areas of pull. When we have a normal, a stretching apart where one side moves down, we have again these areas of pushing that are dark, areas of pulling or stretching where it drops down in the middle. Reverse faults where we have pushing in the middle, you can kind of imagine things are being squeezed together, and stretching on the sides. So when all of these old records were examined in detail, this is the result that comes up. All of these actual red points are areas where the ground went up. Now, unfortunately, we didn't have any offshore instruments. We didn't really have much over here. So we don't have constraints there. But this middle section is pretty robust. And when you model, if you have that type of slip, you go back and compare the modeled, the red to the actual black signal that was recorded at those 2 strong motion instruments. Boy, that fit is really nice, especially when you're talking about really old instruments. So what we can say from this is this was clearly what we call a reverse or a thrust fault. It was actually on a very low angle, 10-degree dipping to the horizontal, and it's oriented almost north-south. That's going to be important in terms of trying to fit it into the various spots it could be. Now, we did have one additional kind of information, which was to revisit the intensities. So Sue Huff spent a lot of time reviewing original newspaper reports, and you've got reports like this that really detailed the damage. And my part was really fun. I got to collect memories of people who experienced the earthquake. I posted a query for information in various publications, including the Times Standard, and also posted on Facebook. And I got about 40 great stories, and I've just summarized a few here. I'm not going to read them all in detail, but this is one of my favorite from the Arcata Bottom. A girl, obviously, all of these people were children. A girl looking out of her kitchen window saw cows from the dairy across the street running across the field. The land was rolling like ocean waves. I suspect it wasn't 20 feet deep, but it looked like that to her. The cows looked like camels, all distorted with their haunches several feet above their heads, as they all staggered to the east in one mass. In Eureka, a huge roar and the shaking began. I recall seeing E Street rolling as we jumped up, terrified. There was a loud crash outside where the top of the chimney had come down. So by looking at these reports, one can actually make estimates of the relative shaking strength, which I've done, the red being at least intensity 7, the yellow intensity 6, the green intensity 5. We could plug that into the process of constructing a new shake map. Now, a shake map is a modern way of looking at the relative shaking strength, kind of like the old isoseismal map, that takes into account actual ground motions and these intensities. And you can see that the general features are actually similar to what was done back in the 1950s. This is on the right, a zooming in, and you can see this area of sort of orangish to reddish in Eureka, in Blue Lake, where we're probably approaching intensity 8 in shaking. The pattern of shaking also helps constrain the depth. When you have a deep earthquake, it tends to be much more uniform at the surface. When it's very shallow, it's extremely concentrated near the epicenter. This pattern is again consistent with with that sort of shallow depth, but not super shallow. So our best guess today is looking back, and again, now this is kind of turning our plates on the side. So North and Oregon is to the right. Here we are, and I'm sitting right about here on top of the North American plate, very close to the Mad River Fault Zone. And as I said, 8 miles or so beneath me is the interface. We can rule out, we think we can rule out, not absolutely, the faults up here, these faults in the upper plate, for 2 reasons. One, they're a little too shallow. And 2, these faults trend north-northwest. And our best orientation of the faulting is actually pretty north-south, which is pretty close to the orientation of the Cascadia subduction zone. We can also rule out faults within the Gorda plate down here because they're too deep and they're all strike slip. As I said, one of the things I think is most convincing about this study is we're looking at a thrust fault. We're looking at something that is dipping shallowly, and in our area, the dip of this interface is maybe 11 degrees, 10 degrees, 12 degrees, which fits very well with our finding. So right type of faulting, it's the right depth, and it's the right orientation. What does this mean? I was super surprised when this popped up because I thought most likely this earthquake was going to end up being another typical Gorda Plate earthquake, a lot like December 20th, 2022, and that somehow the depths just weren't read correctly. The second possibility was, oh, okay, it's on one of these shallow faults. And I would have given it very low odds to be on the Cascadia interface. All of the evidence points there. And it's really the first instrumental evidence for what we call a patch rupture of the Cascadia interface. This red is kind of showing you how big the likely interface in a full Cascadia rupture would be. Down here in yellow is about the size of the 1954 rupture. I mean, it's a tiny little patch, maybe close to the bottom of the subduction zone. Probably not. I would actually draw the subduction zone interface a little bit further to the east, but it clearly did not involve much of the subduction zone. A tiny, tiny fraction. It released almost nothing in terms of the stored strain energy on that interface. The last full Cascadia rupture was in 1700. So it was a tiny player, but it demonstrates that it's possible to have a patch rupture. It did not trigger a larger earthquake on the Cascadia subduction zone. So it was followed by aftershocks, but it didn't trigger a 7 or an 8 or a 9. I mean, it was a standalone event. It demonstrates that these patch ruptures are possible, rare, but they do pose an additional earthquake risk that perhaps we haven't thought that much about, especially for southern Cascadia regions down here, southern Oregon, California, which are basically sitting atop this interface. This study also demonstrates how really important archive data is. Preserve data, even if you don't think it's important to what you're studying right now. Make it available and accessible for future generations. And the whole method of this team is certainly applicable to studying other what we call cold case earthquakes that might yield results that were more interesting than you thought. Right now, we've got a team working on the 1957 Daly City earthquake. This study also brought up a number of really intriguing questions. In the descriptions I got from children, people who were children 70 years ago, time and time again, they talk about observing the ground rolling. Now, back in the late 1800s, the early 1900s, when these intensity scales were first being distributed, ground roll was talked about. And here you can see, even in the original 1931 modified Mercalli description, down here on 12 is damage total. Well, that didn't happen. Waves seen on ground surface, that did happen. Clearly, but basically ground roll hasn't been looked at in a serious way since then. So one of the things I'm getting involved with now is trying to learn more about what are the conditions that produce ground roll. We know that people saw it in the 1992 Cape Mendocino earthquake. We know people saw it in the 1989 Loma Prieta earthquake. These were both shallow earthquakes and they were on thrust or reverse faults. So it's time, these observations suddenly triggered a line of research that we need to look into more closely. The observations of what was happening on the Mad River, I think they were real. There are enough observations of seeing the Mad River slosh apparently flowing backwards, most likely caused by what we call a seiche, which is an oscillation in a body of water. River seiching has been observed before, but it's not well studied or understood. And finally, there were aftershocks, but why have we seen no earthquakes, other earthquakes of this size near the interface in the past 71 years? And if another earthquake were to happen today in that same place, what would we be saying about its potential to perhaps trigger a larger earthquake? So finally, this Thursday is the Great Shakeout, a time to practice what you would do in a real earthquake. And pouring through the old newspapers from 1954 provided a wonderful example of why shakeout is important. Mrs. Fred Hess of Pepperwood, that's not real close to the earthquake, remember, was taken to the Scotia Hospital suffering from 2 broken ankles. During the quake, Mrs. Hess was fleeing her home. On reaching the porch, the shock threw her down the steps onto a concrete sidewalk. Fortunately, she was resting comfortably at the hospital. This illustrates why we want you to stay in one spot while the shaking is going on. If you are young and have good knees and are capable of dropping down to the ground and getting under a table, a desk, and hanging on to it, do so. I'm over here. I'm not in a wheelchair, but I would say that my mobility is somewhat limited. So I'm not getting down on the ground. I'm just going to stay where I am. I'm certainly not going to run out the door. If there's no table or desk, again, making yourself small in one spot. In bed. Fortunately, on December 20th, 2022, almost all of you were in bed. And as a result, you weren't able to get up and run out. And there were very, very few injuries. In a store, well, you got to kind of think about where you are, but even a shopping basket can provide you some shelter. In a theater or lecture hall. So this Thursday is a really good time to think about what you would do in a real earthquake, and perhaps more importantly, going beyond just what you would do, let's seriously start to reduce hazards. Lots of people helped with this presentation, lots of organizations. Obviously, all of the Fickle Hill earthquake team, especially Bob McPherson and Peggy Hellweg. Peggy made it happen, and Bob was sort of the inspiration behind it. I've really been having a fun time going through historical society. I've spent time at the Blue Lake Museum. Sunday, a weekend afternoon, go. It's the most hopping place in Blue Lake. It's really fun to visit. The Humboldt Historical Society, again, on 8th Street, just a great place to dig through the archives. And a super thank you to everyone who contributed their 1954 earthquake stories, and people who happen to have an old diary or journal from a parent and grandparent or other relative that covers 54. Get it to me, because I'm still collecting stories. If anyone has any questions,
We have a number of questions.
Good. Okay.
Richard asks, what do you think of the study recently released about the connection of an earthquake on the Cascadian subduction zone triggered on an earthquake on the northern San Andreas Fault?
Well, fortunately, that was one of the things I wrote about in my Not My Fault column this week. So it was just published yesterday. If you go to the Redwood Coast Tsunami Work Group webpage, we'll have a PDF posted soon so you can read it. If I really encourage everyone, if you're financially able, please support our local media. We're very fortunate to have had so many newspapers on the North Coast for so long. We want them to continue because they're an important source of information. But I've been aware of that group's work for decades. In fact, that study is at least 26 years in the making. But finally, Chris Goldfinger retired. It's good to retire because then you can actually spend time going back and writing up what you've been meaning to write up for a long time. And it's a very solid study. It's not speculative. It's very much based on cores. And in the article, I talk about what a turbidity current is and so forth. But simply, we're always pumping sediment to the continental shelf. Eel River, for its size, carries more sediment than any other river in the contiguous 48 states. A ton of material that's constantly being delivered to the continental shelf. Currents offshore then move it around, and it tends to concentrate at the mouths of our marine canyons. And then when there's enough sediment accumulates, it fails gravitationally and goes in this slurry, what we call this turbidity current, slooshes down the canyon for hundreds of miles. I mean, it's really fluid, and then spreads out on the abyssal plain below. And Chris and his team have been coring the canyons and the abyssal plain, as I said, for more than decades, accumulating these records. And you can then see these distinct currents, turbidity currents, preserved in the sediment cores. Now, you'd expect them to be a random process, because each area is going to be accumulating sediment at a different rate. But instead, they appear to be very much correlated in time. So we have these moments where all of the canyons, from Washington down to Cape Mendocino, they all show one of these debris flows or these turbidity currents at exactly the same time. And the easiest way to make that happen is to have an earthquake that is simultaneously shaking the same area over the same, at the same time. Similarly, a San Andreas Fault type earthquake is going to produce turbidity currents off of the Northern California coast. So what this team did was look very carefully at the time signatures of both, and they found 3 cases where basically there was one turbidity current and then almost immediately a second that even disturbed the first one, right kind of on top. And the only way you can do that is to basically have 2 big earthquakes close together. So yes, it looks like it certainly has happened. It probably doesn't happen every time. We know 1906, that ruptured all the way up to Cape Mendocino, did not trigger a Great Cascadia earthquake. The 3 cases I believe that they talk about are cases where Cascadia has triggered something on the San Andreas, but it's possible that it could happen the other way. Should not be a big surprise because Cascadia and the San Andreas are joined at the hip in the Mendocino Triple Junction. So probably the most important take home for that is that we need to plan for that as a possibility. Our usual approach, if we were to have a Cascadia earthquake this afternoon, and it could happen, would be that all the resources and effort would be going towards responding to communities in Cascadia, certainly the urban areas, Seattle, Portland. Hopefully we'd get some attention up here on the North Coast, but all the mutual aid would be funneled towards the Pacific Northwest. Well, if you suddenly have a 1906 rupture minutes, hours, or a day or 2 later, you're really going to have a hard time responding to both. And so that's something we need to think about.
The other question he had is, do super shear earthquakes occur on the North Coast?
He must have read my article because I talk about both the super shear story and the linkage in my recent and yesterday's Time Standard column. Super shear is really interesting because it's something that was sort of hypothesized as possible back in the 1970s, but it really has only been in the last decade or so that people have been able to observe it. And it really now looks like any very large strike slip earthquake. It's not something that's going to happen in an earthquake like 1954. It's not going to happen on a thrust fault. It's on these long strike slip faults like the San Andreas, like the Anatolian faults in Turkey, where once it starts propagating, because you've got this long zone and it's a large enough initial rupture, it seems to be able to go into that super shear mode. Probably helps it propagate such a long distance. We now think 1906 was a super shear earthquake. Well, I don't, but the people who've researched it. And that's one of the reasons that rupture that began off of where the Golden Gate Bridge is today was able to make it all the way up here to Cape Mendocino. So we've already had the effects of super shear earthquakes, but they haven't really been incorporated into code development as much as they probably should. I was really surprised in researching that for my column, was that they now think December 5th. Part of that rupture was super shear. So that was on the Mendocino Fault. The epicenter was roughly 40 miles off of Cape Mendocino. It ruptured along the Mendocino Fault at kind of normal speeds, sort of slowed down in the vicinity of the triple junction, then continued to rupture suddenly much more rapidly at super shear speeds once it got onto land. How do we know that? Thanks to new technology and thanks to this wonderful optic fiber study that Humboldt County has now become one of the most important instrumental places in the world for studying how optic cables can provide seismic information. And it was purely fortuitous that the team, the USGS team, happened to have that cable network on Old Arcata Road running when the December 5th earthquake happened. And so I don't think there's any way, had it not been running, we would have been able to determine how fast it had been propagating. So it just shows you what an incredibly important time this is right now, with the opportunities of technology that we've got to continue to support, because the best way to live in earthquake country is to really understand the ground motions so that those can be incorporated into codes and we can make sure that our structures are safe.
Another question, where was I? Can you please address the recent unprecedented uptick of large earthquakes in the Western Pacific compared to the relatively quiet on our side?
Well, I always like to say earthquakes are clumpy. One of the most seismically active periods was the early 1950s, as I talked about. We had that huge earthquake in Kamchatka, 1952. We had the big earthquake in South Central California. And then as we continue on, actually the period from 1946 to 1965 was the most seismically active period we've seen in terms of seismic energy release in instrumental history. We had the two largest earthquakes, 1960 and 1964. We had several other earthquakes that were over magnitude 8.5. And then from 1966 to 2004, the largest earthquake anywhere in the world is an 8.4. We have nothing in the upper eights, no nines, between 1966 and 2004. In 2004, we have the Sumatra Andaman earthquake and the Great Indian Ocean tsunami. In 2010, we have the 8.8 Mali earthquake in Chile. In 2011, we have the big Japan earthquake. And then just this summer, we had the 8.8 in Kamchatka. So when it comes to periodicity of earthquakes, we don't have nearly long enough a time record. I mean, we basically have a couple of hundred years of, well, we have a century of good seismic data. We have a couple of hundred years of written data. The Chinese have 2,000 years of written data, but we're looking at just such a tiny window of time. So what I say, what I'm absolutely sure of is that we are one day closer to the next strong earthquake today than we were yesterday. Any more? Hello? Excuse me, I can't hear anybody.
Okay, most of the quakes appear to occur in the most developed zones, such as Eureka and Arcata. Is there some reason for that? Or is it coincidental?
No, that's not true at all. That's where the damage occurs.
Oh, okay.
The damage occurs
okay.
because that's where the structures are.
Okay, that makes sense.
Yes.
Why does gravity pull the Gorda fault under the North American plate? The Gorda plate under the
Well, this would require a whole lecture on plate tectonics. But basically, as plates are formed at ridges, they're very hot. And as they spread away from ridges, they cool down. As they cool down, they become heavier and heavier. And eventually, they become so heavy that they begin to sink back into the earth.
Maybe you can do that in the fall.
Oh, I got to talk about Kamchatka in the fall.
Oh, okay. In 1992, I had my vehicle roll back and forth front to back, east to west during an earthquake. Is this the result of ground rolling?
No, it's just the result of seismic waves. Ground roll is actually slower, and you actually see the ground looks like the ocean. I've never seen it myself. But in all earthquakes, cars are very sensitive seismometers. So even a relatively weak earthquake will cause a car to jiggle up and down. Intensity 3, which if you're walking outside, you won't feel. If you're sitting in a parked car, it will cause you to bounce up and down. It's just because the period of the seismic waves is similar to the sort of springiness of the vehicle. And so even a very weak signal will cause a car to bump up and down.
Well, I was fascinated because it was my first earthquake since we'd moved here of significance. Thinking about the effects of a big earthquake on the Matthews Dam, what do we know about this?
Well, an earthquake is an issue. And there are plans in place for a failure of the dam and what the likely flooded area would be downstream. But this actually brings up another issue, and why I always tell people, if you feel an earthquake while you're on a river, you should move off of the shore. You should move away from the channel, because strong earthquakes, especially on the North Coast, produce landslides. And the larger the earthquake, in other words, the longer the duration of shaking, the larger the potential landslide. There are scars of massive landslides on every river on the North Coast. Landslides that completely crossed the river channel and dammed them. Now, those are unstable dams because the water will accumulate behind the landslide and eventually break through it. In some cases, it may break through very quickly. In some cases, it may take days, weeks, or even longer. You're in no position if you happen to be fishing. I mean, December 21st, 1954 was a beautiful day on the North Coast, and there were a lot of people fishing in the Mad River. Good time for steelhead fishing. And that's why we have these accounts of the river oscillating. If you had been one of those people fishing on the river, I'd get out of the river because it might not make the best conditions for fishing anyway, but you don't know what's happening upstream. And so you just don't want to risk it. You just want to get away from large river channels, especially if that shaking has lasted a minute or longer.
How likely do you think an earthquake could cause significant damage to Scott's Dam on the Eel River?
I'm not an engineer, and all of our structures in California are examined. Certainly some of them are vulnerable. Earthen-filled dams, well, we certainly saw that in 1971 after the San Fernando earthquake, where we had almost a failure of one of the dams. You should really get a good dam engineer to give you a talk on California dam safety, because it really is an important thing, and it's one of those infrastructure issues that is expensive and sometimes tends to be overlooked.
Any other question? Oh, there was one question. Peter asked, what time of day was the earthquake in 1954?
Just before noon.
Yeah, somebody had answered that. Okay. Anybody else have any questions? This has been wonderful. Lori, thank you ever so much. Really appreciate it, and want to let everybody know that next week we're going to have an update again on Life Plan Humboldt, because they've made significant progress, and you all probably want to know about that. So come on back. We'll see you next Monday. And if you have not gotten this week's invitation, please let OLLI know so we can check and see what's going on and try to fix it. Meantime, just know that it's every Monday. You can look online to see, you can get a catalog. We still have them at Wildberries. If you've lost yours, we have them at McKinleyville ENF. We have them at Eureka ENF, a variety of places around the senior center, etc. So go pick yourself up another catalog if you want one. I and others have been busily putting them all over the place where they're accessible, but you can always go online and just see what's coming next. Thanks so much for coming. It appears to have quit raining, so you can go out and about without getting soaked. Have a great
Thanks,
day.
Lori.
What?
Thanks, Lori.
Yeah, we always thank Lori.
Thanks for everybody.
They're exceptionally interesting.
Yeah, and if you know somebody with a 54 story, send them my way.
Oh, okay. I will.